Cycling is a great way to get around, but for some people it can be inaccessible. Luckily, with the invention of e-bikes, it has become more and more accessible to more people. I could talk about the benefits of cycling and e-bikes for days, but I'm not here to do that. I'm here to talk about how e-bikes work. So let's get into it. Let's start by taking a look at the motor, because it's the most complex part and everything else revolves around it. The function of the motor can be split into three parts: the motor itself, the gearbox, and finally the controls to make the motor feel smooth. Let's start by taking a look at the motor. These motors are very similar in construction to the ones you'd find on AliExpress, but they have some notable differences. The wire gauge used to wind the wire is much thicker in e-bike motors. It's around 14 to 18 gauge depending on which brand. Whereas the motor wire used in AliExpress and RC car motors is typically 28 to 32, again depending on the brand. This allows you to push far more current through the motor before the wire starts burning out, as the thicker wire has a decreased resistance. While the maximum power of motors on e-bikes is limited to 0.25 kilowatts, they're typically spec'd much higher, and this is due to a nifty loophole in the testing system. Even with this extra power, they still don't have very much torque, only around 3 Newton meters, which is considerably less than the 85 to 90 Newton meters you get at the crank. So we need some kind of gearbox. Let's take a look at that right now. The gearboxes in e-bike motors differ greatly between brands, but in this Bros motor, it consists of two stages. The first stage is a planetary gearbox with an approximately 7.5 to 1 reduction ratio. The second stage is a belt drive system with a further 4 to 1 reduction ratio, for a total of approximately a 30 to 1 reduction ratio. This is how, from our 3 Newton meter motor, we get 95 Newton meters at the output. Let's take a bit of a deeper look at each of these two stages, shall we? The first thing you'll notice about the planetary gears is that they're not straight cut, and this is because they are a type of gear called a helical gear. With helical gears, instead of the entire tooth engaging at once, only part of the tooth engages at the beginning, and they more or less roll across each other, which significantly reduces the wear on the teeth, but also the noise generated by the gearbox. This planetary gearbox is fascinating, and I wish I could get it out, but it requires specialized tooling, which I simply don't have. If I turn this back gear, we get to see that significant reduction in practice. While I stated this has approximately a 7.5 to 1 gear ratio reduction, it's actually closer to 8 to 1. And that allows us to have a much lower gear. If we have our 3 Newton meters at the sun gear, we're then getting 8 times that on the output, or 24 Newton meters. That then feeds into the belt gear. But unfortunately, this part of the motor, I again don't have the tools to disassemble, so I can't show you that in action. But you could see how a belt could run round that gear and then around this gear, thereby further decreasing the ratio, and that's got approximately a 4.1 times reduction. I'm not going to go into too many details about this, because these Bros motor systems are not known for their reliability. Honestly, I'm pretty sure there are blocks of fissile uranium at critical mass which have more stability than the belt drive systems in these motors. The final cool thing about the gearbox is actually in this shaft here, and I'll show you in a second. But basically what it means is when this motor is turning, you can see how that would be driven by the belt. If I stop pedaling, it will continue driving the chainring, but it won't drive the pedals. And that will stop the motor continuing to drive and smacking you in the shin when you stop pedaling. Something you might not have considered is when we were simply pedaling, if we were having to turn the motor, which obviously isn't connected here, we would have to turn that through our, again, approximately 30-to-1 reduction ratio, which would mean that when we're pedaling, it's going to be very difficult. Luckily, the engineers thought of that, and we can turn our cranks, and there's a clutch in position which allows us to turn the chainring without driving the motor. Hopefully you can see that. I can turn this whole section, and the motor wheel is clutched completely, so it doesn't go in the other direction. If I pop this side out, we can take a look at one of those clutches, and it looks like a series of needle bearings. I've got this out here, and you can see it's effectively a ring of misshapen cams, and these are actually really cool. So how do they work? Well, when we want it to be completely drive-free and be a clutch, we push in this direction, and they go in the correct direction, making them thinner. You can see from the side profile there, they have much thinner profiles, and they basically bypass the walls. However, if we push them in the other direction, they become much thicker. And what that means is they'll jam against the edges of the housing and effectively act as an incredibly high amount of friction. And that will allow us to turn the outside housing with the inside housing, or the inside housing with the outside housing. You can see here that smooth inside housing where that would clamp against, and of course on the other side you can see how it's tightly fitted into this outside housing. You're probably wondering what the heck this Saturn's rings looking thing is on the shaft, and that's a great time to move on to the control, because this is part of the control. It effectively allows the motor to measure both the torque and the RPM of the shaft, which of course will give it then the torque and RPM of your pedals. But how can this possibly give us that information? I'd love to tell you how this works, but first a message from PCBWay. And before you get mad, sponsorships make these videos possible, so a huge thanks to them for allowing me to continue doing what I do. PCBWay offers a huge range of different manufacturing services, with big discounts if you want to buy in bulk. PCBWay is also utilized by many companies you've probably heard of and use on a day-to-day basis. You can check out PCBWay in the link in the video description. Alright, let's get back to the video. It's all about how it's connected. If we look here, this, which is actually the entire drive for our motor, isn't directly connected to the shaft. I'm not sure I can really fit a camera in to show you that in great detail. But what that means is when we apply torque to this, we apply torque to that. And the only way for us to do that is through this thing. But when we do that, it will cause this to deform slightly. So you can see if I do that, it'll twist, and then this will twist at each of those metal points. That'll cause it to move and change its distance from known points, these two bearings. If we take a look in the housing here, we can see these two slots, and those would house two Hall effect sensors, which are basically sensors which allow you to determine the position and or movement of a piece of metal. This shaft is held in position by these two bearings, so when this deforms, the Hall effect sensors can tell us about the deformation, and thereby, using complex equations based on the known strength of this, tell us the torque that's being applied at the pedals. I really wish I had the control board to show you how it works, but I don't. I don't know where it is. So remember how I just said I didn't have a control board? I've actually gone out and purchased one off eBay so that we can have a look at this. So let's get started and look at some of the components. On the left side here, we have what's some kind of voltage shift. This is allowing us to have the correct voltage for a lot of our components, which run at a lower voltage than the 36 volts this motor takes. That's one of the interesting things. But another thing you'll notice is on the front we have 6 MOSFETs here. And those 6 MOSFETs are basically the motor driver itself. Each MOSFET is either the positive or negative side of a 3-phase inverter. Let's explain 3-phase inverters real quick. This is a simple single-phase inverter. When we turn one of the MOSFETs on, it will connect the power to either positive or negative. If we turn the top MOSFET on, it connects the output to positive. If we turn the bottom MOSFET on and the top MOSFET off, it turns the output to ground. Obviously, if they're both on at the same time, this is bad, so I can add a little bit of gate drive circuitry here, which allows us to turn them on and off at different speeds. I'll explain that in another video. Now if I put 3 of these phases together, we get a 3-phase inverter, which can be controlled by these 6 wires on the left. There's actually a little bit more going on here than just this, but that's way outside the scope of this video. I can explain it in another one. If you want to see that, just let me know in a comment. Anyway, let's get back to the control board. The final thing we'll notice before we flip this board over is these 2 sensor pillars here. And these house our Hall effect sensors, which detect both our torque and our RPM, as I mentioned earlier. Right, let's take a look at the other side now. There's not a huge amount going on this backside, but there are a couple of things of note. If you see here, we have this huge exposed metal area, and that's basically allowing us to cool the circuit board, and thereby, on the other side, I'm assuming, yep, we have our MOSFETs. So we can cool that by connecting it to the case with some kind of thermal compound, which you can actually see there are traces of still all over this. The only other thing on the backside is this processing unit, and that's basically the brains of our motor. I can't really read what this is, but I'll see if I can put it on screen later on. This basically acts to take all our data in, compute it, run it through the special motor algorithm, and output the correct power for our brushless motor, which is connected on the other side to these 3 connections here. And that's basically it, except for this, which is the signal out to our control. That's our thumbstick or our display, which gives us a lot of information. But most interestingly, this actually has a 48 or 36 volt pin, which sends the power from the motor directly to the screen. And that's because the battery monitoring is done using the processor in the screen. That's pretty much it though. There's not a huge amount going on here. Technically, you could leave at this point, because that's the end of the explanation of e-bike motors. However, I wouldn't recommend it, because I'm actually going to be talking about my big project this year, which is another hand cycle. I know, boring. But this time, I'm doing a lot of things differently. Most notably, once I finish it and complete all the designs, I'm going to make it open source, so you can build the hand cycle yourself at home if you have the tooling. As part of the sponsorship for this video, I utilised PCBWay's sheet metal cutting service to cut these end caps out for my frame. And this allows me to build my frame much more cheaply than it would be if I CNC'd it. I welded these onto 1-inch aluminium tube, and that allows me to have a really nice, compact, but pretty nicely designed frame, utilising this 3-tube design. Anyway, that's it for me, and I'll see you again soon.